Hello, my name is Juan Sanchez Torres. I am a graduate student in computer science at Roosevelt University. This presentation is mainly a description of some of the methods I have implemented in order to provide empirical evidence for a yet-to-be-published research paper concerning Cnf formulas, isomorphisms, and distances between them. We also discuss the issue of parallelizing these methods and some partial results for very small formulas. What is a propositional formula? A propositional formula can be thought of just as a proposition, that is, an assertion regarding a fact. This assertion can be true or false. A little bit more formally, we can say that a propositional formula is made up of clauses, which in turn are made up of propositional variables or literals. These can only take on one of two values, true or false. We represent these values as 1 and 0 respectively. A literal is any propositional variable or its negation. A propositional variable and its negation are complements of each other, since they cannot both be true at the same time. If x is true, then not x is false, and conversely. An assignment for a formula is a function from its set of variables to 0 or 1. In other words, we assign a value, either true or false, to each variable x in the given formula. When we have assigned a value to all the variables in the formula, we evaluate whether the formula as a whole turns out to be false or true under that particular assignment. A formula that is always false is referred to as unsatisfiable, while a formula that is true under some assignment is referred to as satisfiable. The decision problem considering whether a given formula is satisfiable is called the Satisfiability Problem, and it is abbreviated as SAT. The search or counting problem concerning the number of satisfying assignments for a particular formula is called the Counting Satisfiability Problem, and it is abbreviated as sharp SAT or counting SAT. What is a clause? We consider a clause to be a non-empty finite set of literals containing no complementary literals. C1 as constructed here would be a clause since it contains two literals which are not complementary, while C2 cannot be considered a clause since it contains both x1 and its negation. Additionally, we consider a clause to be a disjunction of literals, that is, we apply the logical operator OR over the literals of the clause. Therefore, C1 can be rewritten as x1 or not x2. We consider that an assignment satisfies a clause if any of its literals is true under that assignment. Of course, this follows from the logical behavior of the OR operator. So for example, the clause C1 is satisfied under these three assignments. We can now discuss formulas in a more formal setting. As noted before, a formula can be thought of as a finite set of clauses, or a multiset. For example, phi can be a set containing both C1 and C2 where C1 and C2 are clauses. This view amounts to thinking of a propositional formula as a combinatorial object, similar to a graph. Additionally, we consider a formula to be a conjunction of its clauses, that is, we apply the logical operator AND over its clauses. Phi can be rewritten as C1 and C2. We then consider that an assignment satisfies a given formula if and only if it satisfies all of its clauses. For example, consider C1 to be x1 or x2, C2 to be not x1 or x3, and phi to be the formula containing both C1 and C2. Phi is satisfied by any assignment under which both C1 and C2 are satisfied. One such assignment is presented on screen. We now go through some useful notation. We consider that a formula phi is only valid if there are no gaps in its set of variables. That is, if phi is a formula containing a single clause which contains in turn only two literals, this clause cannot be written as x1 or x3, since we do not have three literals. Instead, it should be rewritten as x1 or x2. The size of a formula phi is just its number of clauses. The width of a clause is again the number of literals it contains. If the maximum width of any one clause in phi is k, we call phi a k-Cnf formula. So for example, if the maximum width of any one clause in phi is 2, we would say that phi is a 2-Cnf formula. The set of variables appearing in phi is denoted as var of phi. We mentioned the notion of isomorphism between propositional formulas. When do we consider two formulas to be isomorphic with each other? Informally, we consider two formulas to be isomorphic if one of them can be obtained from the other by only renaming variables and flipping, that is, changing the value of the literals. Consider phi1 to be x1 or x2, and phi2 to be not x1 or not x2. From phi1, we can map xi to not xi for I equals 1 and 2. Equivalently, we can flip both literals in phi1. If xi was 1, map it to 0, and conversely, for I equals 1 and 2. In both cases, the resulting formula is indeed phi2. Thus, phi1 is isomorphic to phi2. Now consider a different pair of formulas, psi1, which is just x1, and phi2, and psi2, x1 or x2. There is no way to obtain one formula from the other only by flipping literals and renaming variables, because we cannot map two variables into one. Thus, they are not isomorphic to each other. We can also see evidence of this fact in that psi2 has 4 possible assignments and is satisfied by 3 of them, while psi1 only has 2 and can only possibly be satisfied by 1. Having done the review on propositional formulas, I now present a bird's-eye view of the system I have implemented. We establish a maximum formula size m, a maximum clause width k, and a maximum number of variables n. We want to generate all possible formulas of size at most m with at most n variables and clauses of width at most k. We want to identify all different isomorphism classes in the space that has been defined with our constraints. We want to identify as well all formulas as either representatives of an isomorphism class or members of an isomorphism class. After this, we'll process the generated data to visualize statistically significant relations. For example, the number of isomorphism classes in this space, the number of formulas per isomorphism class, the distance between class representatives, or the SAT and sharp SAT status of each representative. We rely on the notion of isomorphism to think about how similar two given formulas are. Thus, we can say that we are interested in a measure that allows us to discuss how close or far two formulas are from being isomorphic with each other. A notion of distance between pairs of formulas could serve this purpose if this distance is preserved under isomorphism, meaning the distance between phi1 and phi2 should be the same as the distance between any two formulas psi1 and psi2, where psi1 is isomorphic to phi1 and psi2 is isomorphic to phi2. We now briefly expand on the general notion of distance. Consider a set X, a function d mapping ordered pairs from x to the non-negative integers is a distance function if for all elements xy of x, d of xy is equal to d of yx, and d of xx is 0. If this is somewhat unclear, you can place it in the context of 2D Euclidean space, what we usually call normal space, and we can imagine as a sheet of paper. Of course, the distance from a point A to a point B has to be the same as that from B to A. Similarly, the distance from a point A to itself is of course 0. We recall the notions of metric and pseudometric. Consider the following two restrictions on a distance function d on a set X. For all elements x, y, and z of the set X, if the distance between x and y is 0, then x is y. 2. The distance between x and y is less than or equal than the distance between x and z plus the distance between z and y, which is the triangle inequality. If d satisfies both 1 and 2, we say d is a metric on X. If d, however, satisfies 2, but not necessarily 1, we say d is a pseudometric on X. If this is somewhat unclear, we can think of it in the context again of Euclidean distance in 2D Euclidean space. Consider 2 points A and B such that the distance between them is 0. They have thus the same coordinate and are at the same point. A equals B. Consider now a right triangle where the line AC is the hypotenuse and AB and BC are the remaining sides. The restriction 2 necessarily follows from the Pythagorean theorem. Euclidean distance on Euclidean space, then, is a metric on Euclidean space. We can see that whatever function we define as a distance on formulas, we need the distance between two isomorphic formulas to be 0, since they are as similar as it is possible. Additionally, two isomorphic formulas cannot be said to be one and the same formula, since they are not necessarily logically equivalent. Thus, the Cnf distance function is and has to be a pseudometric on the considered space. We now give an informal account of the distance function for pairs of Cnf formulas. This distance can be described in terms of superformulas and subformulas. Roughly speaking, given two Cnf formulas, phi and psi, we say phi is a subformula of psi if phi is contained in psi. Conversely, we say that phi is a superformula of psi if psi is contained in phi. Consider now three Cnf formulas, phi1, phi2, and theta. Let theta be the largest formula such that both phi1 and phi2 have subformulas isomorphic to phi. Then phi is a maximum size common subformula to phi1 and phi2. Conversely, let psi be the smallest formula such that both phi1 and phi2 are isomorphic to subformulas of psi. Psi is then a minimum size superformula. The distance between phi1 and phi2 can be thought of as a difference between the size of theta and the size of psi. We recall now the notion of symmetric difference for pairs of sets A and B, since it is the basis of the distance function. Recall that the symmetric difference for pairs of sets A and B is the union of A and B without the intersection of A and B. In this slide, we can see both the multiset and graph representations for two formulas. We will return to the conversion from multiset to graph representation at a later point. For now, consider phi1 to be a formula on one clause with a single variable, x1, and phi2 to be a formula on two clauses and two variables, the first clause containing x1 and the second clause containing x2. The distance between these formulas is of 1. From looking at their multiset representation, we can intuitively understand a little bit why. They differ just by a single element, and in fact, if we take their symmetric difference, that is, if we first consider their union, which would be x1 and x2, and take out their intersection, which is x1, what we get is just a single element, x2. The cardinality of this which is 1, hence their distance is 1. It is important to note that xi is isomorphic with not xi. Consider two formulas, both containing a single clause and a single literal, one containing x1 and one containing not x1. Their graph representations can be seen on screen. We can see that the only difference is that the node labeled C1 in one of the graphs is connected to a node labeled x1, whereas in the other graph, the node labeled C1 is connected to the node labeled not x1. Now this is a difference only in labeling, which means that by renaming the nodes, or in fact by renaming the variables, we can get one formula from the other. Thus, they are isomorphic. In this slide, we can see the formal definition of the distance function for pairs of Cnf formulas. As stated previously, this distance can be shown to be a pseudometric on the formula space and to induce a metric on isomorphism classes. We take these claims as true. The decision problem associated with the Cnf distance, which we have called the Cnf Distance Problem, can be stated as follows. Given two Cnf formulas phi1 and phi2 and an integer d, determine whether their distance is equal to d. This problem can be shown to be NP-hard via a reduction from the Hamiltonian path problem. We take this claim as true, but we present a reduction from formulas represented as multisets to graph representations of set formulas, which gives some intuition of the ideas needed for the proof. Before describing the algorithm for formula-to-graph conversion, let us consider what we want to achieve. We want to generate results that empirically support the notion of a Cnf distance that is isomorphism invariant. For this, we need to be able to identify isomorphic formulas. Additionally, for our results to be empirically meaningful, we need to work within a predefined space, which we need to map. Specifically, we consider the space of all two Cnf formulas with a maximum size of 6 and a maximum number of variables of 6. We need to be able to bin all isomorphic formulas into a single isomorphism class and generate all isomorphism classes over a space. We then compute the distance between isomorphism classes and store statistically meaningful associated data. For achieving identification of isomorphic formulas, we can consider their graph representations and check for graph isomorphism. Similarly, we can use a formal definition of isomorphism between formulas and check for isomorphism directly on the multiset representation of the formulas. In this presentation, we will only examine the procedure in which we use the graph representation of our formulas. The first thing that we need to consider for our formula-to-graph conversion procedure is how to actually construct a graph given a multiset representation of a formula. That is, we need to describe the specific reduction to graph that we will use to encode Cnf formulas. Let phi be a Cnf formula. We consider both clauses and literals as vertices with different properties. For each clause Ci in phi, we add a node Ci to our graph. And for each literal in the set of variables of phi and their negations, we add 3 vertices, somewhat like adding 3 copies of the same vertex, and we connect them so that they form a triangle. This is done so that we can always differentiate between clause vertices and literal vertices without having to introduce different colored vertices. Since for clause vertices there will never be a triangle such as the one between the 3 vertices that represent a literal, we will always be able to tell whether a given node or set of nodes represents a clause or a literal. For any literal xi and any clause cj, if xi is in cj, we add an edge between xi and cj. And for any literal xi, we add an edge between xi and its negation. Note that the construction described in the past slide preserves isomorphism. We will now go through an example conversion. Suppose we are given a formula phi with two clauses, x1 or x2 and x3 or not x4. The size of phi is 2. The set of variables in phi is the set containing x1, x2, x3, and not x4. The set of their negations would be not x1, not x2, not x3, and x4. Clause 1 is x1, x2. Clause 2 is x3, not x4. The width of both clauses is 2. We want to construct a graph G such that G is the graph representation of phi following the procedure outlined in the previous slide. We start off with the graph G with no vertices or edges and our formula phi, x1 or x2 and x3 or not x4. We add the nodes labeled C1 and C2 representing each of the clauses. For each literal xi in the set of variables of phi and the set of negations of the variables of phi, we add 3 vertices. Then we add edges between them such that all 3 vertices representing a literal form a connected triangle. Recall that the variables of phi and their negations are x1 through x4 and not x1 through not x4. We thus add 24 vertices to our set of vertices. Then, for each pair of complementary literals, we add an edge connecting them. In this slide, we see 3 different ways of representing a formula phi. First, the multiset view. We can view phi as a set containing 2 sets, the set containing x1 and x2 and the set containing x3 and not x4. Equivalently, we can say that phi is x1 or x2 and x3 or not x4. We have as well the visualization of the graph G representing phi. We now consider the procedure for checking for isomorphism between pairs of Cnf formulas. Given 2 formulas, phi1 and phi2 in their multiset representation, we construct their graph representations, G of phi1 and G of phi2, according to the outlined procedure. We use the iGraph library to generate graph objects for the graphs G of phi1 and G of phi2. This is done in order to use the graph isomorphism solvers included in the library. We check if G of phi1 and G of phi2 are isomorphic. If they are, then phi1 and phi2 are also isomorphic and belong to the same isomorphism class. Otherwise, they can be considered to be in different isomorphism classes. We utilize the isomorphism check described in the last slide to identify and populate isomorphism classes. Let phi be a formula. The isomorphism class containing phi is the collection of all formulas over our space that are isomorphic to phi. Thus, this class can be considered as phi up to isomorphism. Assume for now that we have already generated all 2 Cnf formulas over a certain space. Let us call this set of formulas F. Even though we have already generated them, we don't know anything about isomorphisms between them or the distances between them. We want to identify all isomorphism classes in this space and partition our set of formulas accordingly. In order to identify all isomorphism classes and correctly populate them, we define an empty 2-dimensional structure, specifically a dictionary, where each entry will be a pair, x and t of x. X is the first formula that we find for a certain isomorphism class, and we call it the representative of that class. T of x is the set containing all formulas in that space that are isomorphic to X, including X. That is, T of X is the complete isomorphism class. We can identify representatives and populate the isomorphism classes following the procedure that I will now sketch. For each formula F in our set of formulas, we define a counter and initialize it to 0. This will help us verify whether a certain formula is a representative of a new class or a member of an existing class. We generate the graph representation of f, g of f. For each representative r in the keys of our dictionary, we generate the graph representation of r, g of r. If g of r is isomorphic to g of f, we increase our counter by 1. We then add f to the isomorphism class for which r is a representative. Otherwise, we move on to the next representative. That is, we continue to the next iteration. If our counter is 0 after iterating over all representatives, then f is not isomorphic to any of the currently known isomorphism classes. Thus, f is a representative of a class. We add f to the set of keys of our dictionary. Recall that in the description of the isomorphism class identifier algorithm, we assumed we already had a complete set of formulas over the specified space. Of course, we need to be able to generate every formula in that set. So how should we proceed? We need to choose a representation for the formulas. Thankfully, we already have formulas expressed as sets of sets, which is an adequate representation for our purposes. Working with the graph representations, as we have constructed them, would be more computationally expensive and somewhat cumbersome. Intuitively, we can see that we can generate different formulas by combining different clauses because formulas are built up from clauses. Thus, we need to generate clauses first, and then do a sequence of combinations on those clauses to generate formulas. Starting with the next slide, there will be a change in notation for the sake of clarity. Given that we will be working on the multiset view of our formulas, I will shorten xi to just be represented as an integer I. Thus, a formula with two clauses, the first one being x1 or x2 and the second one being not x3, would just become 1 or 2 and not 3. This is done to simplify expressions and to better capture the operations that we need to perform. Additionally, working with arrays of integers makes more sense for us than working on some other object that could represent a literal. Of course, clauses contain literals, but since we have changed the representation of a literal to simply be an integer, we do not have to worry too much about generating literals. Rather, we can use the maximum number of variables we allow as a boundary on the interval of integers over which we will work. That is, if we know that the maximum number of variables allowed is n, we immediately have the list of all possible literals, which we call L. This list would be the set 1, 2 up to n, union -1, -2 up to -n. Given L and a constraint on clause width k, we can generate all possible clauses by first generating all possible subsets of L with size at most k. Recall that in our case, k is equal to 2. Note, however, that simply generating all possible subsets of size at most k over our list of literals L will not give us exactly the set of all possible clauses. We need additional restrictions. For example, one of the subsets returned by a method which generates all possible subsets of size at most k over L would be the set containing 1 and -1, which is not a clause, since a clause is defined not to contain complementary literals. Thus, we disallow all subsets of the form I, -I, directly when generating subsets. If we are working on a space over more than one variable, then we will generate a subset, for example, like the one containing only the literal 2, where the name of the literal surpasses the actual number of variables present in the clause. A set like this is problematic in that if we treat it exclusively as a valid clause, then we would need to add a formula which contains exclusively that clause. That is, at some point, we add the formula containing the clause x2, or 2, to our array of formulas. But this is not actually a different formula from the one containing a single clause containing the literal 1. We cannot, however, simply disallow the generation of such clauses, like we did for clauses of the form I, negative I, since we need such clauses to generate formulas like the one containing two clauses, one with the literal 1 and the other with the literal 2, which is just a combination of the clause containing 1 and the clause containing 2. Thus, since we pretend to generate formulas from subsets over an array of literals, we need to make sure that every formula we generate is shifted to be of the right form. That is, before adding a generated formula like the one containing two literals labeled 1 and 3, we need to rewrite it as 1 and 2. We can sketch a clause generation procedure as follows. Given the maximum number of variables n and the maximum clause width k equals 2, create a literal array L containing 1, 2 up to n and -1, -2 up to -n. Let CL be an empty array where we will store all possible clauses. We add every element in L to CL. They stand for clauses of width 1. Then for I, from 1 up to the cardinality of L, and for j, from I up to the cardinality of L, if the absolute value of I is equal to the absolute value of j, that is, if I and j are complementary literals or the same literal, we continue to the next iteration. Otherwise, we add to CL the pair I, j. We will now consider the generation of formulas over a specified space. For intelligibility, we will assume use of Python's combinations method in iter tools. Combinations takes in an iterable object, in this case the array of possible clauses CL, and an integer r, and returns all subsets of size r of the iterable object given. Once we have populated CL, we can use combinations and a boundary on the size of formulas to generate all possible formulas over the specified space. We can sketch a procedure for generating formulas as follows. Given a clause array CL and a maximum size m for formulas, we define a variable fl to be an empty array where we will store the generated formulas. For I equals 1, 2 up to m, and for each subset C in combinations CL of size I, we call a candidate formula F, and we say that it is the set containing C. Recall that C will be a concatenation of a number of clauses. We need to ensure C is parsed as an array of set clauses for it to be a candidate formula. Then we rewrite F as F without gaps. We will not cover the gap elimination method in this presentation. We then add F to the array of formulas FL. We now consider a procedure for computing the distance between two formulas. Evidently, the distance between any two formulas in the same isomorphism class is 0. Thus, we only need to concern ourselves with class representatives and not the complete formula array. Given two class representatives, phi1 and phi2, declare a counter and initialize it to 0. For each clause CL in phi1, if CL is an element of phi2, then increment the counter. Then the distance d between phi1 and phi2 will be the size of phi1 plus the size of phi2 minus 2 times c. Basically, every method described in this presentation runs in polynomial time. However, since we are dealing with combinatorial processes on multidimensional arrays, we have several instances of nested loops. The amount of formulas, even in a reduced space, is staggering and grows very quickly. For example, we recently estimated the number of formulas in the space of two Cnf formulas with a maximum of 6 variables and 6 classes to be around 50 million formulas. Thus, a system such as the one described in this presentation stands to benefit a lot from running certain processes in parallel. The procedure described for the generation of formulas is very naturally parallelizable. Recall that the outermost loop in the procedure changes the size of the formulas being generated and added to FL. Effectively, we generate all formulas of size 1 before moving on to size 2, and so on for all values of I. Thus, we can simply define a process which generates all possible formulas of a fixed size. There are two key modifications of the original procedure to get the parallel version. 1. Our original formula generation procedure takes in two parameters, the array of clauses and the maximum formula size. The new procedure takes as parameters the array of clauses and a fixed formula size. And 2. The outermost loop in the original procedure is removed in the parallel version. Once we have defined the new version, which we call P, of the process, and assuming we have access to at least m processors or threads, where m is the maximum formula size to consider, we run m copies of P with parameters CL and fixed size of 1, CL and fixed size of 2, up to CL and a fixed size of m in parallel. After all m copies of P are finished, we put all m generated arrays into a single array, which now contains all possible formulas in the space defined. We note that the final parallelized version of the system will still have parts executing sequentially. This cannot be avoided given the nature of the problem we are trying to tackle. We presented a procedure which allows us to identify and correctly populate all isomorphism classes for a given space. As presented, there are important aspects of the procedure which cannot be parallelized straightforwardly since we rely on the sequential generation of partial results. Specifically, we rely on previously identified representatives to identify more representatives. Separating the nested loops involved in this into different parallel processes would result in errors either in the identification of representatives or in the assigning of a class to its isomorphism class, since we will have no guarantee of the order in which the isomorphism checks are occurring. Running the parallel version formula generation procedure and then running the single process version of the isomorphism check procedure does in fact improve performance, but it is not ideal. There is, however, a relatively simple fix for this that relies on an equally simple observation. If two formulas are not of the same size, they cannot be isomorphic, and thus belong to different isomorphism classes. Therefore, we only need our isomorphism check to be sequential when dealing with sets of formulas of the same size. We can define a similar procedure as we did for the parallelization of formula generation that checks for isomorphism only on formulas of a certain fixed size. Such a procedure would only identify and populate all isomorphism classes over a small section of the complete formula space. However, since correct identification is guaranteed by our observation that two differently sized formulas will never be isomorphic, we can very easily combine the results of each partial isomorphism scheme into the complete determination of all isomorphism classes over the complete formula space. As of the time of the writing of this presentation, we have generated and processed data concerning the very small space of two Cnf formulas with at most 2 variables and a maximum size of 2 clauses. we found that in this space there are 8 isomorphism classes with a total of 31 formulas. We describe some of our results in more detail in the next 2 slides. In this slide, we can see the moments for some of the relations of interest for us. In terms of number of formulas per isomorphism class, we found classes containing 8, 4, 2, and 1 formulas, with the most common number being 4. In terms of number of satisfying assignments, we found classes with 1, 2, or 3 satisfying assignments, with the most common number of satisfying assignments being 1. In terms of distance between pairs of representatives, we found pairs of representatives at a distance 1, 2, 3, and 4 from each other, with the most common distance being 2. In these last 2 slides, we can see the plots corroborating the results that I have described on the previous slide.